So today, so last few classes, I think Professor Sen has told you about data sets and their features and what could be possible directions in which we could look at problem statements. And then I covered a few of the unsupervised learning algorithms. So we have covered supervised some bunch and unsupervised clustering as well as, let's say, dimension reduction. Yeah. So today we are going to talk about something like which is useful in the general practice before we jump on to the rest of the things. And specifically, they're useful because you are starting your project. So I thought to bring it earlier a bit. So this will help you in some regards. Some of the things I might have already spoken, like while I'm doing things. However, some of the things might come as new. Yeah. So the goal here is like in general machine learning practice, what we do is let's say uh, I give you a problem or you have started your own problem and you want to use machine learning for it. So, but some of the steps that you have to apply, let's say before ML work can actually start. Specifically, I hope you remember when we put like model is equal to logistic regression and then model dot fit. Yes, the model dot fit is what finds parameters for your model, right? Like the W and B is the moment you write dot fit function, that is the place where the model finds the parameter. But before you do that, there are a lot of other things that you should give a try. And those are written here. And we'll go over them one after another. Uh, so, because sometimes when you apply the model, let's say somebody told you this is the best model to be applied in this kind of data set, and it's not working for you. And most of the times, and I can tell you like 99.9% of the time, it's because these things have not been handled. Yes. And so the things are basically one of them is called feature engineering. Yeah. It's a very fancy term, but we will go through some of the things that are there. And algorithm selection, of course, which algorithm to select. We have talked about this in briefly while we are discussing this entire course. And then handling something called overfitting. I have used the overfitting word in a lot of slides, but I have not exactly told you what overfitting is. So today we'll cover that, and then hyperparameter tuning and performance assessment. Yes. And performance assessment, some parts have been covered by Professor Sen. I also covered some parts, but today we'll just make it a little bit more formal. The slides remain to for you to come back. And as I've told, like even before doing the dot fit, these are all the things that has to be done. Yes, if you look at any GitHub code in for machine learning that has been used, either if that is like a closed model, like as in nobody wants to share anything, they will specifically they would like to hide these parts like feature engineering, algorithm selection, and how did they handle overfitting, hyperparameter tuning. Nobody will tell you. Yeah. So because they know that this is the cream of the entire thing. Even if I told you like SVM, let's say support vector machine, is the best algorithm for this. If I don't tell you any of these previous things, you will you can try like random things probably, and maybe you will hit, but to find immediate answer it will take a very long time, right? So people generally hide these things, but as a research paper, as a research community, we should keep on sharing these things as well. Yeah. So the next is, let's say one of the examples here was, let's say we need to predict, let's say whether a particular customer will stay with us or not. Yes. And we want to find out based on the logs of customer interactions with our product, let's say for 5 years. Yes. So we have 5 year data and we have logs of customer interaction, and then yes. Uh, then the next thing is like I asked you to find out prediction. So you thought, okay, so this is machine learning and prediction. Let me just use some linear regression and directly on top of this data, right? So, but uh, it's we just cannot grab the data and just load into a library and then get a prediction, right? The primary first task is to build a data set. Yes, we need to make sure there is X. We need to make sure what is Y, and if they're in proper format or not. Yes, that's entire finding all of these is basically called feature engineering. Whatever raw data you get, if you convert them into informative feature vectors that enable learning algorithms to predict models. Yes. So raw data, two features. Yes. Uh, that's feature engineering. Yeah. So now, mm, let's say we have, yeah. So let's say we have this collection of labeled examples, let's say xi and yi. Yes. And each element is now xi is a feature vector. I'm just repeating some of the things we have done. So every example looks like xi comma yi. We have n number of them, and every xi, the ith dimension of that particular, let's say xi will be the feature vector, and that particular feature vector can have like each dimension will have something, let's say d-dimensional feature vector. Yes. And the value itself is called a feature. Hmm. And for most of the practical problems, generally this feature engineering is what takes the maximum amount of time. Yes. Now, for example, let's say this transforming logs of user interaction, right? So we wanted to predict, will the user stay with us or not? So we just have logs of user interaction with the computer system, right? And how do we start with it? So we can start creating features for it, features for our data set. So that can contain, let's say the feature can contain something about user itself and some statistics from the logs. We just cannot feed the log. Okay, this time period there was a click, that time period there was something else. So these are very varied, let's say, data points. Yes, we cannot use them. Rather, we build or engineer the features that goes into data set, right? So we could ask, like, some part of the features should tell us about the user itself. Some part of the features should tell us about the interaction in form of some kind of statistics. Let's say how, like per day how many connections was made, per week or per year, those kind of statistics we can keep, right? And if we are taking like per second, then we are like, and then we could also add average session. Yeah, how much an average session lasted and all this. So what is the goal? The goal is to just not make any random thing that we find in the data as a feature. Rather, our goal should be to make or find as many as informative features as possible. So informative is the keyword here. Right? So features, though we have understood, features we have to convert from raw data to features, but just not any features. Rather, we want to create which have like higher information, right, to give us. So, and these informative features would allow basically the learning algorithm to build a model that predicts very well for the, like, during training and also after training. Yes. And these highly informative features are also called features with higher predictive power. Yes. Uh, and because they have higher predictive powers, you could go that these are informative features as well. Yes. For example, let's say the average time we spent, like, it's not that how many times I clicked on YouTube, rather how long I am spending on YouTube. That is a more informative feature than how many times YouTube actually opened. Right? And similarly, I think YouTube's ad revenue also works on similar. It's not that you opened the YouTube video, rather how long did you actually see the YouTube video. Based on that, money is calculated. Basically, our interaction time. Hmm. So that means we understand people come to the YouTube and spend time so that YouTube can show ads in the middle. Yeah. So same way I told you, like for example, customer retention, these are things. So subscription price, like economic commitment, login frequency tells us engagement level, session duration tells us how satisfied the user is based on the quality of the video. Let's say, for example, response time, system quality, of course. Like if you click on YouTube, how quickly it loads, right? All of them, like some of them are user related, some of them are system related, and we could also add features like, for example, user is from where, like India or like USA or like Europe. Yes. So all these could become some quality and informative items, right? And this all does not come randomly. Rather, this is where majority of you will come into picture as, like, domain knowledge experts. So you understand material science very well. Based from there, you pull. So even if the data set is too large, you have to figure out what gets filtered to features, whatever that can give us most information. Yes, this is where the domain comes into picture. So, and the key insight, very nicely written. So everything measurable can become a feature, but not everything should, right? uh, that's the way we go ahead. So I hope This has translated well to you for your problem statements. Not everything the data is useful. You have to select. Okay? Now, the first thing that we do in feature engineering, along with finding informative features, is the next thing is something called one-hot encoding. Yeah. So here, what happens if like some learning algorithms will only work with, say, let's say, numerical feature vectors, right? So they will only take numbers as input. And if we had categorical features, let's say colors, here is red, yellow, and green. Let's say days of the week, Monday, Tuesday, Wednesday, Thursday, and let's say weather is like sunny, like uh, and then rainy. Yeah. So all those are, let's say, categorical, but your input, like your model's input or even output also sometimes, they expect numerical values, right? And majority of the algorithms, they do require numerical inputs, right? We understand numbers more. Yeah. So what do we do? So the first idea is we can do something called a one-hot encoding. This is basically we convert the categorical feature into binary vectors. Yes. So here, for example, if you see, we had three possible choices. Like that particular feature, the column itself has red, yellow, green, 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 yellow. It has one of them, like either red or yellow. Each observation, each row will have either red or yellow or green. We have to replace that because that is in text format or categorical format to numerical format. One way to do, I told you, like one-hot encoding into like binary vector. So here we can give like red will be 100, yellow will be 010, and green will be 001. Yes. And by doing this, what do? We increase the dimensional dimensions in the feature vector, right? Earlier it was just red, red is just one value. Now it has become three values, 1, 0, and 0. Yes. So your dimensions increases. But just to save dimensions, we should not do red equal to 1, yellow equal to 2, and green equal to 3. I hope like you can guess the reason also. Because if I put 1, 2, and 3, it makes that like 1, 2, and 3, there is an order between them. Like after red, yellow will come, after yellow, green will come. And then green is very far from red, like 3 minus 1 will be like 2, right? So it puts an inherent, like implicit distance between these values, which was already not there. Like we added this noise if we pick red equal to 1, yellow equal to 2, and green equal to 3. Yes. So that's why choosing this binary conversion like 100, if you look at the distance, everybody is like distance of, let's say, 1 or 2 as you calculate. Yeah. So that's way useful. So this is one-hot encoding. It's super useful. Still we are using this. Yes. So you can understand how useful this is. But this has one demerit I told you, the dimensions increase. Yes. So if there are too many values, the number of dimensions will increase also too much. Now, uh, what happens if is there a case, like the question was, is there a case where we could do 1, 2, and 3? So there might be like ranking, let's say rank 1, rank 2, rank 3, rank 4. If that is there, we could do 1, 2, 3, 4. That is allowed. If let's say it is like wavelength, let's say rainbow, all those seven colors, let's say if there are there and we expect that to have a ranking, we 1, 2, 3, 4, 5, 7 could still work. Yeah. Because original data also had that distance. We are just putting that distance. And sometimes those kind of 1, 2, and 3 instead of using one-hot encoding can help the algorithm learn faster and better as well. Fine. So that is one-hot encoding. So given categorical features, we want to convert into numerical inputs, we use one-hot encoding. The next is, what if we are in the opposite situation? Let's say we have categorical features, but we want, oh, sorry. So we have continuous features and we want to make sure that, but the program expects to be categorical. One of the process to do so is called binning. It's also called bucketing. So it's basically it divides the entire continuous feature into multiple bins or buckets, and typically based on the value of the ranges that we have. Yes. So for example, like instead of like representing age as a single value feature, let's say from 0 to 15, it can have anything. Then the point is the amount of scope of the model to predict lies from 0 to 15. Instead of that, we could then bin them. So bin here is like we have binned from 0 to 5 is one bin, 6 to 10 is one bin, 11 to 15 is one. So we could tell ki, okay, the age, if it is 7, it lies in the bin number like 1. Yeah. So here the usefulness is, of course, we tell ki where it's not the exact value printing, rather in which range it is there. Like sometimes we don't even require this, right? We are like, let's say medium salary, low salary, high salary. So for us, if we find that, that is okay. So then why pressurize model to predict the exact salary? Yes. And then sometimes if the noise happens, let's say like salary was not exactly, somebody wrote 26,520 instead of 520, it shows like 27,520. If we do this binning and ranges, sometimes those noise in exact calculation also mismatches because we are anyways blurring the boundaries. Yes. And of course, it is more interpretable, like by telling that your credit score was exactly 520, rather than if I tell, okay, your credit score is in the low range. So people understand it better. Yeah. So that's the thing. So algorithms learns the exact age does not matter within these ranges, right? So, but just the range is important. And also another thing, so this binning, like a very careful, like well crafted binning can help algorithm learn in very few examples also. Yes. So you can, if you can do binning really nice, it can actually help algorithm learn faster and better. Yeah. Because sometimes it can give you a hint which range, but it can go other way around also. For example, let's say there are a lot of, let's say a lot of values around, let's say the number 10. Yes. And somehow, like as in if you have a Gaussian curve, let's say, and most of the values are under this particular mean value, but you somehow made that, okay, if in the left side of the mean is something else and the right side of the mean is something else, but the better classification would have been like mu plus sigma and minus sigma, that is a range, and rest of them could have been other range. That would have been better. But if we split in the middle and we say, okay, everything less than mean is something else, anything greater than mean is something else, then we are basically forcing the algorithm, like we are giving a wrong hint. Instead of a positive hint, we gave a wrong hint about what is like good or bad, or what is positive or negative. So it could also backfire also. So binning, when you do, again domain knowledge is necessary on when to bin. Yes. So both a weapon, and it could go bad also. Yeah. So now next, so we understood a one-hot encoding, we understood binning. The next one is normalization. Yes. So normalization is a very standard process of converting the actual range of values, which a numerical feature can take, into like a standard range of values, right? Specifically, let's say for an example, with a range of like 0 to 1 or minus 1 to 1. Right? And that depends on the formula that you use. Yes. Now, for example, let's say the natural range of a particular feature, let's from 350 to 1450. Let's say we try. What we do is we can subtract 350 from everything. Yes, and whatever. So we do an x is, let's say, between every number lies between 350 to 1450, and then we subtract 350 from it and then divide by, let's say, 1100. Yes, that will basically do a normalization. Yes, and the minimum and maximum value will lie within the range of 0 and 1 here. Yes. So why should we normalize? So normalization, I think we have discussed along in the other previous classes on how it affects the algorithms. But just to repeat, so first though, is normalization always necessary? But no, technically the algorithms that have been built into sklearn or other good libraries, let's say, they already assume that it is data is not normalized. So either they include that in the process itself, like their own packages and libraries will already have it inbuilt. So it might not be super necessary. But it also like tells you that don't depend on library's source code. They might not have done it also, right? That is where you could do. But otherwise, nowadays, like generally libraries are like good enough. Yeah. So now where can it help? So first of all, I told you about the age and the salary difference. So any large scale feature, the feature which has very large range or which is has a very high value, that will not dominate because every feature has been normalized to values between 0 and 1. Right? So that is one advantage. So that large scale features don't over dominate. Yes. Then like numerical stability, because I hope this one, I think some of you might know. So like in a computer, if a number is represented, it is represented by, let's say, let's say I will tell in bytes. Let's say like some of the one byte, let's say for example, 4 bytes are represented, let's say one floating, let's say decimal point number. Yeah. But as if you understand, like the decimal point number will be, let's say, 16 digits before the decimal. I'm just giving an example. So 16 digits before decimal and 16 digits after decimal. Now the point is the precision of, let's say, if we had 10 digits of precision, then either we can focus on the, let's say, 10 digits of be after decimal point, or 10 digits before decimal point, or a 5 and 5. All these are decided based on the range of the number that we have. If all our numbers don't have decimal points and everybody is, let's say, high, then it's way easier. But if, let's say, we have numbers of 16 digits, but our precision can only lie between 10 digits, then we are in trouble, right? But if we do normalization, then every number falls below 0 and 1. And we can just understand, key, okay, we can just increase the decimal number precision. Like after decimal, we can just have 10 digits of precision. This is what called numerical stability. So this also is very helpful. Yeah. And fair comparison, I told you, like in KNN, K-means and everything, wherever distance is calculated across features, uh, and like within features, but the sum is done across features, let's say, over dominance won't be there, and each feature will contribute proportionally to the distance between them. Yeah. So that's where normalization is nice. The next comes standardization. Standardization is it's also like z-score normalization. So something similar is done, just a little bit. We still want to reduce, let's say, values, but we are shifting the mean and variance. Yes. So it is the procedure during which the feature values are basically rescaled. Yes. Rescaling is also done in normalization, but here rescaling is a little bit so that the properties are basically, it resembles the properties of, let's say, normal distribution where mu is equal to 0, sigma is equal to 1, and the formula is given by this. So you subtract the mean and then divide by the variance. Yes. You can ask a question now, if standardization is z-score normalization, when to use what, right? So I don't have a very strict answer to that. Some of the based on some of the books, this is what is the general recommendation. So if it is unsupervised learning, uh, generally you can use standardization. If the data itself is normally distributed, then you could use standardization. And if there are outliers, because outliers can spoil things. If you see the normalization, if all the numbers lie between 0, 1 to 100, but there is one number that is 1 million. If I do normalization, then my 1 million becomes 1. Rest all the numbers are 0. Within 0.000 and 0.0001, right? So then that's the issue. So here standardization can help that if there is an outlier, it will not consider that, that can remain as an outlier in this after standardization also. So in that way, it's super useful. And so unsupervised learning standardization, normally distributed data standardization, and presence of outliers. If you expect, then you can do standardization. Yes, you can always plot the figure. Now you know how to find outliers also. Yes, and then normalization is for any other cases. Yes. As I told again, most of the algorithms are generally robust to different scales now. Most of the libraries come with that, but reprocessing definitely helps and is something that you can control, so better habit. Yeah. Now the next thing that we're going to discuss is, so we discussed 4 things today, like one-hot encoding, binning and bucketing, normalization, and standardization. And the next thing is, let's say you have an entire, let's say a table, and there are some things that are missing from the table, right? So that means data set has holes or pockets. We don't have data. Either data was not collected, it was missing, a sensor went bad, something or the other, right? There are missing values. So what do we do? So the idea is either first thing that we could do is we can remove entire rows. Let's say if one row has one missing value, we can just remove the row, entire observation, because that observation does not have that particular value. But the problem with this is if we have only, let's say, 10 rows, if we remove that one row, we have 9. That is too less of a data. So this can be only tried when you have a too large number of data sets. Yes. And generally, when like data sets that we discuss from good sources, what Professor Sen has discussed, they generally will always come with this handled. Yes, but typically when you generate for your lab and your PhD, these might not have, like you might miss some values. So this might come in handy. Or otherwise, the second step is one, you can remove rows. Second step is like you can use algorithms that handle missing values natively. Yes. So some of the learning algorithms, they can like basically deal with missing features automatically. Like particularly sklearn can the sklearn has some things that accept nan basically or zero values, so they can do that. Yes. The other thing is basically what you can do is called something called data imputation technique. So this is also used quite a while. So what we do is given like if there is a table is given, few of the cells have missing values. If you have to replace like because they're missing values and you want to add a value there, so you could replace it with the mean or the medium of that particular column of the feature. Yes. And or otherwise we can replace with an out of range value. So that means it particularly tells ki, okay, this was either a noise or it was a missing value. That can also be done. Or we replace with something called a middle, like the mean of it, let's say middle value of a particular range if we have. Or what we could do is we could apply a machine learning algorithm to predict that missing value. That means given all these input points, like rest of the input points, let's say, okay, so just me be careful. So let's say there are 5 columns in your input data set. There are 5 columns, let's say 100 rows, and you have to predict, let's say, one Y, one column of, let's say, 500 rows. Yes. So this 5 columns that we have, let's say one of the columns is was very noisy or let's say missing features. Yes. What you can do is, let's say for those who are not values, you can take them into test, and those who have values you can take into training. You understood? So like we are not touch, we have lived y completely away, so we only have x. In x there is one column that has missing values, few missing values. That missing value column has now become our new y. Yes, like temporary new y. So given the rest of the 4 columns as our x, this being y, everything that is missing values we put into testing, and everything that is not there that has values in the y column will take this as training. So earlier 5 columns in x now becomes 4 columns in x, and a temporary y we created based on the last column or last or whichever column has missing values. So we could use then any regression algorithm, let's say KNN or let's say linear regression, to predict those values based on the previous 4 plus 1 to 4 plus this 1 of missing values. Yes. So that is another technique that is also very useful. Yeah. So excellent. So I think this is data imputation. Uh, this is basically advanced imputation that I was telling. So you can treat the missing feature as a target variable, use the remaining features as predictors, and then train regression model on the complete examples wherever it was there, and then you predict for the missing values. Yes. Uh, so like those are the things, and binary feature for example was actually the original value missing. So for example 0 or 1, it's very tricky, and what you can do is you can replace the missing value with 0 also, or chosen constant. Yes. And generally algorithms are also okay chasing, okay, 0 we understand probably it is missing. Yeah. So I think this one is a nice guideline for you all, that if you use an imputation technique for training, please make sure you add the same imputation for prediction as well. This gives more uniformity whenever you present, let's say, a paper or research paper. This question generally comes. Yes. So what imputation technique if you use for training, use the same thing for prediction data. Yeah. Fine. So now, given that, the next step is basically how do you choose an algorithm, right? So this is like we have looked at around 7 or 8 algorithms now, or maybe we have looked at more than that. So around 10 algorithms, let's say. And so which algorithm to choose, right? So and the answer is always like to try all of them, yes. But given we all have limited time, PhD or MSc, wherever we have, trying all of them is not possible, right? So then we basically ask few questions to ourselves before choosing. The question is explainability. So is like, does our algorithm needs to give explainable guidance to non-technical audience, right? So generally most of the algorithms that we have, like more accurate algorithms that give like very high accuracy, they're generally black box models. Black box models means like it's very hard to understand, like, and to explain as well as interpret. I think I explained the definition of interpretability and explainability both last class. So black box models are this, but they make very few errors. Yes. So if explainability is important, then we will not be able to use those black box models. Rather, we have to go to interpretable models. Rather, those are like linear regression, let's say KNN, decision trees. These are very simple to explain. Like, why did you get a result like this? What was in the input that gave you this result? And interpretable also, like what part of the model basically was responsible for the output. The next is computational constraint. So this one comes from in-memory and out-of-memory dataset. So how to explain? So I think we have covered like say KNN. KNN, for example, that algorithm is not trained, right? So that algorithm just takes the data, asks the question on data, and gives you the answer. There is no training process involved as such, right? So with that, we have to choose because then KNN would like to have the entire data on the memory because you are not training on it because and it's asking the question to the entire data set. So that'd be like in memory. Out of memory would be like training has been done separately, it has come and you have to only test. That means data set does not remain in memory while you are asking a question. So this would be like out of memory. Yeah. And also that depends on training speed, prediction requirement. We learned about TISNI and UMAP. I hope you remember. So TISNI takes a lot of time, UMAP is faster. So based on that, yes. And there are some algorithms, some names, this is a very general case also, like some algorithms will take a lot of training time, but the prediction will be fast. There can be some algorithms which train very fast, but take a lot of time in prediction. These can happen. Yeah. So we have to give a choice on that. The next thing is like how many features we have, how many examples we have. Based on that, we have to select things. More the complicated the model is, the more the features or examples it will require. Uh, like for example, neural networks, and we'll discuss some ensemble methods. They can handle a lot of examples. But some of the algorithms like SVM and others, they don't scale well with the features and examples. Yeah. The next question to ask is categorical and numerical. This, though, I think you are clear most of the things now. Like, what is the output expected, regression or input? Or input is categorical or numerical. What to do? And then linear and non-linear. This we have also discussed a few times. If the data is linearly separable or distance boundary can be there, then please use linear model. It will be super fast. SVM is there. Logistic regression, linear regression. Those are very nice choices. If not, then we have to use non-linear algorithms, right? Like example was like PCA and UMAP testing. Yeah, fine. So the next step comes as a basic idea, just training and validation and test sets. I talked about this a bit in the earlier, but just formally stating, there are three, generally we expect three sets to be there: training, validation, and testing. Training is what you use to optimize the W and B of that function. Yes. Validation is where you optimize the hyperparameters, right? So for example, in decision tree, let's say we have to build a decision tree, you use the training data set to find out what will be there in the each node of the tree, like which features question we will ask. But in the validation set, we'll ask what should be the height of the tree. Yeah. And the test, of course, we don't touch. We just use that to report our output, like what accuracy, how good the model is. Yeah. And so this just shows a very generic output like 70%, 15%, and 15%. Is there a guideline to it? Generally, no. We will talk about a bit about this a little bit later, but generally there is no strict guideline. The more the data you have, the more the data in training, of course, is better. The more the distribution of the data we have in training is even better. Yeah. So why do we need three sets, first of all? So the way I told you earlier, like sometimes what happens that we can have a validation set, let's say training set, and we can perform really well in training. And somehow by fluke also we can perform with the testing also pretty well. But sometimes we want to verify with a third party. That's why like validation came into picture, right? So for example, if your lab exam, there is a Viva component as well as actual lab component, right? So why do we do this? Because maybe in lab exercise, we are lucky to just get the titration done properly. Like maybe yeah? You do not know the procedure. That's why we have a Viva to make sure that actually you knew what you did. Yeah. So similar example of validation and testing. So the next thing that we have is something called underfitting and overfitting. So yeah, underfitting and overfitting. So here we will discuss two things. These are very important. Something called a bias and something called a variance. Okay? So definition is very simple. I'll just sorry. So bias basically means if if the model makes many mistakes on the training data set, that means it has a high bias. Okay? Or we tell basically the model underfits. Yeah. So here it is also similar to the definition of inductive bias. Basically, we tell that the eventually like high bias models will make more errors. So that's why it is, and low bias models, because low bias models basically make less assumption about the data, and high bias models make like strict assumption. Like linear regression would be like a high bias model. Neural network, which we will cover, is a low bias model. Neural network does not make any assumptions about data. Linear regression makes a very strong assumption that data are linearly related. Yes. So in that sense also you can relate, but the definition of bias here particularly, it just says ki if you make a lot of error in your training data, that means you are underfitting. Yes. And you have high bias, of course. Yes. So what is underfitting? Underfitting is the inability of the model to predict well the labels of data it was trained on. Like the training time itself, it is performing poor. Yes. So reasons are model is too simple, or the model is like it does not. Oh no, so the model is too simple, and the second thing is like the features that you have selected are just not good enough to give you answer. Both the things can happen. Okay, so this should be a clue. So whenever you are underfitting, that means you are giving a lot of errors in your when you train, and your training loss is too high. So you can come back to this. Either the model chosen is too simple, I should increase the complexity of the model, or my input data set does not have enough information to give me the output. Fine. So this is underfitting. Very nice. Like if you follow this principle, you can like solve this issue. And then overfitting is high variance. Yes. So here, oh sorry, I'll just show an example. Yeah. So if you see the middle one, so it says all the points in the graph, and we have like a very nice curve that is the actual, let's say, good fit model. Yeah. So that's how the pattern it follows. Underfitting because we chose a very high bias model. That means it takes very strong assumptions about the data, which is linear, uh, and it gives a lot of errors in the training set. So it is underfitting, right? So on the left hand side, the red one. Yeah? So it's a linear model, it's a high bias model, and it does a lot of error, right? You see, the prediction is far away from the actual. Yeah? And then comes the overfitting. Overfitting is something called like high variance also. And The overfitting, the definition is simple. So here we say like the training performance is really well, but the validation test performance will be bad. Yes. But the definition of overfitting or high variance is uh, if the variance is basically the error of the model due to small changes in the training set. If I change the training data points slightly, for example, here, if you look at this example, all these points are here. Please look at the orange line. I'm trying to do mouse, but well, yeah. So all these points that are there here on the on the right hand side building. So this is a basically overfitting like model. If I change one data point, like if you look at one blue point, if I remove it, no, the model will change considerably. Yes, that's all it says. That if I change the data points even minutely, the model changes by a very large amount. That's basically causes high variance. Yes, but that is high variance. And if it shows high variance, then it is overfitting. So great, it will show great training performance, but it will show poor validation performance. So similarly, if you see the model is very clearly, it's trying to copy exactly how the older one is. It will work great for the training set, but if you put some additional points, it will fail badly. That's what overfitting is. Now, once you have overfitting, that means training loss was good, but testing loss was bad. What do you do? Yeah. So here you can do two examples that are here. Like model is too complex. That means you have used, let's say the model was linear. Like for example here, if you see the polynomial regression, let's say we have degree 2 is actually a good fit, but we are using degree 15. That means degree 15 is like too complex. You have to reduce the complexity of the model. You have to reduce it to, let's say, 2-degree polynomial. Yeah, that is one. So SVM, let's say you have support vector machine, you are using RBF kernel. Instead of using RBF kernel, you can use linear kernel or quadratic kernel, something less. In neural network, we'll cover, but not now. So that you can do. The other thing is basically you have too many features and too few examples. That means the number of columns are too high compared to number of rows, number of observations. If that happens, this can also be a problem. So if too many features are there and too many few examples are there, so what do? We have learned the technique last week. We can do dimensional reduction to reduce the number of features. Yes, that is one idea to do. Yeah. Or we can increase the number of rows. Yes, for example, if you have found a very nice data set, but it has only, let's say, 100 rows but 1,000 features, you can assume that it will overfit. Yeah. So what we can do, we can dimensionally reduce the 1,000 features to, let's say, 100 features, or we can find other data and then could increase the dataset size. Yes. Or we could do oversampling. All other techniques are there, not for today. Yeah. So there are few other techniques involved as well. But just to before I cover there, so this one, so increase model complexity, use sophisticated algorithms, add polynomial features, increase neural network depth. We'll cover them. This is the solution to underfitting. And otherwise, we could improve features like more feature engineering from material science domain. We can add something more, change something more, or we could collect more relevant data, as in like feature itself. Yeah. So for example, one example is if you want to predict cancer with just height, blood pressure, and heart rate, doesn't matter what model you use, the feature itself are like very clearly insufficient, right? So we will never be able to predict. So it will underfit anyway. Overfitting, reduce model complexity, use simpler algorithms, fewer neural network parameters, we'll cover neural network when it is. And then shallower decision trees, like reduce the height of decision trees. And then database solution, you could collect more training examples, dimensional reduction of the features, and what features are good also. Instead of like, for example, if you have 1,000 features, you can cherry pick which features are important. That will also reduce the dimension. Yeah. And there is one thing that comes into play is called something called regularization. Regularization does nothing, just reduces models complexity. Yeah. Uh, and this is a very widely used approach to prevent overfitting. So if overfitting happens, you can look at these two things. Regularization is also another set of techniques, basically it envelope set of techniques which basically help you reducing model complexity. Nothing. So here we'll just go to regularization basically. So now what happens here? So even like simpler models like linear as such, they can also overfit the data, right? Because maybe the model itself is linear, some parts, so it can do a linear fit also. Specifically, it happens when the data is very high dimensional and the number of training examples is relatively low, let's say. Now, in this, what we can do, basically, the linear learning algorithm can build a model that assigns non-zero values to most of the dimensions. Yes. Uh, Now, this is a super complex model and it will predict really poorly. Yeah. So what do we do? Because it has assigned to non-zero weights to most of the features, it will eventually lead to, because some of the features are definitely not necessary, but it has applied some weights to it. So what do we do? That process of reducing the complexity in this is basically regularization. Yes, and there are many methods to do this regularization. Yes. So regulation, if you can understand, it reduces the complexity. That means in practice, like we increase the, uh, it reduces the complexity. Uh, so here, what happens is the bias or the bias will increase, right? So the more the complex the model was, that means it was open to like no assumptions about the data. The moment you make it less complex, let's say from SVM RBF to SVF linear, let's say we count linear, SVF linear expects that there is a linear separation. So we are reducing the complexity, but the bias will increase. Yes, but that minor change in the bias will significantly reduce the variance, and variance is what is overfitting. Yes. Now, this particular, you can increase the bias, let's say that will reduce the variance. And if you increase the variance, that will, let's say, reduce the bias, right? So what is the best model you could have? Something that has super low bias, low assumptions about data, let's say. That means it does not make a lot of errors in training, and something that has low variance also. So low bias and low variance is what we want. But generally, what you have in those like stock is basically either it will be low bias or high variance, or high variance and low bias models. So if you can look at this as a like a four, like a box, low bias and variance will be somewhere here, and then you will have low bias and low variance. You will have, let's say, low bias and high variance and low bias. Yes. So our goal is to somehow move this here. But anything that has high bias and low variance, we can apply regularization to move it towards low bias and relatively mid variance. So it will try to move towards low bias and no variance. Yeah, that's what regularization does. Yeah. And there are two very popular methods. One of them is, let's say, L1 regulation, other tool L2. Popular names are lasso and ridge. These are very similar to what we have done before in some other things. But if you can see, like if you can see on the right hand side of the equation, there is, if you see just the right hand side of the equations, they are just like MSC loss, right? So these are prediction minus the actual whole square and then their mean, like sum and their mean. I'm taking an average. Right hand side does not change. And if you see on the left hand side, there is minimum W and there is a C associated with it. C is again that controls how much regulation we want. Yes. This is very similar to the hinge loss that we did. I hope you remember that. So this is the one which controls this, like either the weight will be high or this one will be low. Yeah. So this is lasso and ridge regression. If you see the difference between lasso and ridge, the only difference here is one of the weight here is like the L2 norm, the other one is just the absolute value. Yeah. We'll come back to like what probably differentiate between these two. But generally, if you understand, if I put C is equal to 0, that means no regularization has been applied. This becomes the original MSC loss. But if I apply some regularization, like means C has some value, then it becomes some regularization. I'll talk what happens. But if I, let's say, put very high value of C, what happens? MSC loss, it will not care. It will just care how, because I want to minimize CW, or let's say L2 num of W. So I will try to reduce the values of W to as minimum as possible. Yes, that means if a particular feature, like every weight is associated with a feature, right? So I'll have W1 X1, W2 X2, W3 X3, let's say. Now, if I have CW and I want to minimize it and C is very high, what I will have, that W1 I will try to reduce, W2 I will try to reduce, W3 I will try to reduce. Yes. And uh, either it will reduce to a very small value or to like zero. And if it becomes zero, then that particular feature, doesn't matter, the feature has some value, the W associated with it is anyway either zero or super small value. Yes, that's the difference. And so in that way, if you see, the W is what decides the model complexity. The number of weights I have in the model is what decides the complexity in the model, and also the number of features as well. If I reduce, if I put a C that is very high value and the W is there, if I increase the value of C, most of the W's are basically pulled down to zero. That means most of the features that are there, their weights associated with it become zero. So they become, basically, we can ignore them. Yeah. So that means model now becomes highly biased towards few features. So we increase basically some biasness, but we reduce the variance. Yes. This is how basically both L1 and L2 regulation works. And these are very classical way of doing regulation. The only properties are like L1 regulation, it will create very sparse model, like it will end up with weights to be zero, and it automatically does the feature selection. And of course, once the features are completely dropped to zero, like the weights will be completely dropped to zero, it becomes super interpretable, right? Because only few features will be responsible for final output. Yes. The only problem is because it's like CW, it's linear, so it is non-differentiable at zero. Yeah? But L2 regularization, like all the weights stay, nobody becomes zero because it's like no, sorry, yeah. So, and then it has better predictive performance. Generally, L2 is like a little bit preferred. Uh, and then differentiable everywhere, and it has computational advantage also. Then there is additional term. Because L2 is like, if you can see, sorry, if you can see L2 has this like L2 norm, because it is there, it is easier to differentiate. Yes, and you can find exactly, you can, because otherwise here, if you find differentiate, it becomes C, which is like non-informative. There it basically tells the gradient will have an output with W. Yes, so it tells how much to reduce based on the actual value of W. So there is another regularization technique, the elastic net, which basically combines L1 and L2 regulations. Yes, and there are other regularization techniques as well. We will cover them during like neural networks. These are called dropout, batch normalization, layer normalization. These are all very nice techniques that we'll use. Uh, there are also something called like early stopping, which technically not known regularization, but these are also helpful. Fine. So the next one is performance as already. I'm just adding a few here to make this slide complete. One of them is if you want to assessment as in how do you tell if the model has performed really well or not. So this is on testing output. One is the MSC loss itself. So you compute MSC on training set, MSC on test set, and you compare those two values. Ideally, we would expect the test MSC to be closer to training MSC. We will know it underfits if training MSC is very high. We will know it overfits if testing MSC is very high than training. Yes, because it is MSC, of course, we can only do regression here. Yes, because this is only for regression output. This is not categorically predicting. Yeah. Now, if we find test MSC to be better than training MSC, that means overfitting, then we apply all the overfitting techniques that we learned previously. For a regression, there is also R2 score. This one is also very useful in most of the, at least we have seen in biological domain, so this is super useful. You predict this one, so like what we have is like if R2 score should lie between 0 and 1, let's say anything like between 0 and 1 is very nice. Not very nice, like above zero point 0.5, what did you expect? Like generally it's acceptable around 0.7 or something. 1 is super good, 0 is a baseline like equal. Like it is like the model is as good as predicting the mean. Yeah. And if the model is even worse than telling it as mean, then it becomes negative, right? So that is how worseness is calculated in R2. And in classification, I think processing covered few of this. So I'll just go. You have confusion matrices like true negative, true positives, false positive, false negative. Yes. So for example, if you have true positive, if it was a spam and you identified it as a spam, true negative it will be it was not a spam and you identified as not a spam. Yes. And similarly, false positive and false negatives you have. So if you make that as a table, if you can look at this small, like the algorithm monospace fonts, like spam, actual not spam, spam and not. Something is predicted, something is actual, and you just take like which values, like how many were actually spam and you predict it. Yeah? And two positive is like basically if it was a spam and you predicted a spam, and similarly true negative not a spam and you predicted not, and anything else false negative and false positive. So that is confusion matrix, and after confusion matrix, you end up with precision and recall. Yes, and this is also super useful. Um, of course, like it is like precision is two positives divided by total positives. That means like out of all the predictions that we made that these are the spam, how many were actually correct, right? This is in contrast to how many actually true positive we had across all. But what we are saying that these are very useful in like biological domain, specifically the sensitivity and all. So if we predicted, let's say COVID, everybody, like if we predicted everybody as COVID, we would be 100% correct in predicting at least COVID, right? That if we tell like who are COVID positive, we can tell everybody is COVID positive. That means we are not missing anybody, but that's not the point, right? Then the precision will be very high, but then recall will be very low in that sense. Like we can just tell whatever we have predicted, everybody is actually COVID positive. Sure, but that's not very helpful as well. But rather, we also want to find out like if we had predicted amount of these positives, how many were actually positive, right? From actual positives, if we had some actual positives, how many were we able to predict? That would be like recall. Yeah. So one of the simpler examples, Christian would tell me of all the returned documents that we have, how many were relevant, and recall would tell you among all the relevant documents, how many relevant documents you spread. So those are a little bit different things, Christian and recall, and usually you cannot maximize both of them. Yes, so they have a trade-off between each other. And example, let's say high precision will basically avoid blocking legitimate emails. Yes, if you make it high precision algorithm, then legitimate emails will not come to you. If we have low recall acceptable, then some spam in inbox will come. Yes. Medical screening, I told you, like high recall, you don't miss diseases at all. Low precision, that means some false alarm, even if it comes, we can resolve it. So based on that, we choose either it has to be high recall or low precision. Yes. How do we adjust which one to go ahead with? Like we adjust class weights, we modify the decision thresholds, we do the hyperparameter optimization. All these will affect recall and precision. And also accuracy, I think we have discussed this, like we have already discussed previously, like how much we were accurate. Yes. But that does not always give us the right answer. Like, uh, so precision recall are sometimes very useful. Yes. And we can have cost sensitive accuracy also, like a weighted accuracy kind of thing. So here, basically, for example, if false positive is important, so we can increase the cost of finding a good false positive. Yes. If missing a spam, let's say one or two emails come to your spam, it's not important, we can reduce the cost. Let's say earlier it was, let's say, how do I say, accuracy is like TP plus TN by, let's say, two positive plus two negative by summation of all, we can say 1.5 TP plus 0.5 TN. That means two negatives, we have reduced the value, 1.5 we have increased the weightage. So that's how we can do cost sensitive accuracy based on what we want. And the next thing that we have is ROC AUC curve. Did I put the picture? Sorry, I forgot to put the picture here. But I'll. So here we basically do a plot. Let me just show you. Sorry, I know it's like 5:37, but like give me like 2 minutes. Okay, I hope you can see this. Yeah. So this is the ROC AUC curve. Yes. So this one basically is a let me sorry. Yeah, I hope this is visible. What it says is basically a plot of true positive rate with false positive rate. And ROC AUC curve you can have between true positive rate and false positive rate. But there are other ROC curves also that do it with, let's say, precision and recall, and there are other stuff also. But this one that I'm showing you, it is between true positive and false positive rate. A true positive rate would be true positive by true positive plus false negative. That is same as recall. False positive rate is false positive by false positive plus true negative. Yes. And this construction, this will vary the distance threshold. So what we are looking for is area under of curve. If the area under the, sorry, if the area under the curve is 1, that means it is like a this and this. That means true positive rate is super high, right? So that's basically area under curve is like 1. And if it is in the middle, like the AUC curve is like 0.5, that is like as good as like a random classifier. Yes. So anything AUC above zero point 0.5 is what we would expect, and more closer to 1 will what we like, and rather than closer to like less than 0.5. Yeah. And now let me see. Yeah. So I'll just show you another small figure. Yes. So sklearn has a very nice, I hope this can see. Yeah. Yeah. So, and sklearn has a very nice diagram, you can reach to this one. So this is based on general practice, might not be like only thing that you do. It just says that you start here. If the number of samples is greater than 50, then you are you predicting a category? Then it's a labeled. Are you is the data labeled? So if you're predicting a category, as in you are predicting like something, and you have a labeled data. If you don't have a labeled data, then you go to classification. But if you have labeled data, go to classification. If you don't have labeled data, you go to clustering. And in clustering, let's say, is the number of categories known. Then you go to the left hand side, you find like k-means and all that stuff. If it is not known and the data samples is there, then you do this or do that. So it's a very nice flowchart that has been given based on where you could start. Okay, so I will put this in the slide and then I will upload. So this is a very nice slide you can follow for your project, let's say, or wherever you're doing. But this should not be the only thing that is there. That comes with experience, and like all the previous papers that you will study, they have already gone through this and they have found out that this might not have worked and they might have tried something and eventually they landed up here. Yeah, fine. So I just want to end. So today what we did, so today we basically covered how do you, before doing model.fit, what do you need to do? One is feature engineering, making sure informative features actually come in a proper way, one-hot encoding, binning, bucketing, the same thing, and then normalization, standardization, filling up the missing uh, values. Then how do you select algorithm? Like what are the problem constraints? I showed you the sklearn diagram that is helpful. how do you split the data, training, validation, testing, and why it is done so. And then regulation we covered few topics like lasso and ridge. Where are they useful, where not to use them, and then there are some other advanced techniques, but we'll reach to them. And performance assessment, MSc R2 square for regression. Accuracy, precision, recall is some of the classification metrics, but there'll be many more as well as we go ahead. Yes. So overall, models, data, features, metrics, there is models have their own loss function, cross entropy, maximum likelihood. I hope everything now is coming into picture. And then from the next class, we will move a little bit deeper and slowly into a little bit more complex algorithms, let's say. Not super complex, but little bit complex based on whatever we have studied till now. Yeah. That's all for today. If there are any questions, please let me know. Sorry, I haven't checked the chat if there are any. Yeah. Okay. If there are any questions, otherwise the slides will be up. Please have a look, and hopefully you will get to practice all of these soon in your projects and any work that you do. Yeah. Okay. Thanks a lot. We will meet on Monday 4:30. Yeah. Bye.